Okay, hello. Today we are going to be taking a look at this particular question from carboxylic acids. So this is the class assignment question, which was a past year A-level question, November 2016, if I'm not wrong. Okay, so this is a synthesis problem, and it requires you, instead of drawing out the synthesis scheme, they draw out the synthesis scheme for you already, and then you just need to state the reagents and conditions and draw the structures of the intermediates. Okay, technically, if you are very, very used to drawing out your synthesis scheme the way that we have been drawing it out in tutorial, um, the way that we've been um, showing you the thought process on the board with the arrows and everything like this, if that's the way that you are accustomed to answering synthesis problems, then can you technically just copy out this entire scheme and then fill in the blanks? Yes, you can. But since they've already drawn it for you, I highly suggest you don't waste your time copying. Just write here nicely step 1, step 2, step 3, step 4, and then just draw the intermediates that they want. Okay, so please don't waste time drawing out the entire scheme again if they do not ask you to. And then, so these are going to be my 4 steps, and then I need to draw the structures of M, N, and P. That was a bit ugly, sorry. Okay, so first, in this particular case, you remember how I've said before in synthesis problems that you do not always need to work from left to right, right? Sometimes you can also work from right to left. So in this case, the ultimate product is Q, right? Let's look at what are the functional groups that are present in Q. Obviously, the one we're interested in is there are actually two amide linkages here. One here, N C double bond O, and then one here also, N C double bond O. So we have said that this is an amide. Sorry, amide. And we know that an amide is formed from condensation. That's why we have this arrow here to show that it's this thing, and P will undergo condensation in order to form my amide. Now, this compound over here, this is obviously an acyl chloride, right? Your COCl group. So think about it. What is the other thing that undergoes condensation with an acyl chloride to form an amide? We've just covered this in this topic on carboxylic acids. Obviously, this is going to be an amine, right? More specifically, it's supposed to be a primary amine. So we know by working backwards that this is an acyl chloride, this is an amine, and then we can think further back. How can I prepare an acyl chloride? Maybe this is acyl substitution, and maybe this is a carboxylic acid. Let's see if this is plausible. Okay, so I start from cyclopentene, which is an alkene. So remember, always think about what functional groups are present, what functional groups convert to other functional groups. Because really what your R is really not that important. It's about what your functional group is. So this one is an alkene. Oops. Alkene. Okay. And just to clarify at this point, right, in case this particular scheme is a bit unclear, it's not that cyclopentene undergoes one reaction to produce two products, is that cyclopentene can either undergo this to produce M, or it can undergo this to produce N. Okay, so think what are two reactions that an alkene can undergo? There's not that much, right? You only know two things that an alkene can undergo. One, of course, being your electrophilic addition, and the second one obviously being your oxidative cleavage, right? These are the only two types of reactions that you learn in alkenes, what topic 11. So we know presumably step 1 is either EA or ox cleavage, and then step 3 is going to be the other one. But which one is which? We've already said just now, right? I have an acyl chloride here. What can I use to prepare an acyl chloride? Maybe this is a carboxylic acid. Now let's think, okay, alkene to carboxylic acid. Can I use one of these two reactions to convert alkene to carboxylic acid? Obviously can, right? Oxidative cleavage of an alkene gives you a carboxylic acid. So maybe this is step 1. So therefore, we know that the reagents and conditions for oxidative cleavage are going to be KMNO4 dilutes H2SO4 and heats. Don't put under reflux, huh? I know when you, by now that you have gone through alcohols, carbonyl compounds, you may be very, very used to writing heat under reflux. But you see that your lecture notes, they actually write it like this, is then heats, and then you put the under reflux in brackets like that. Okay, just to clarify at this point, what does this under reflux mean? This means that I hit it with a reflux setup because you've done your practical 16 already with the organic synthesis. You know that the purpose of a reflux setup is so that any part of the reaction mixture that condensate that evaporates will just condense back into the flask. So you minimize the loss of the reaction mixture. So the cases in which you will need this under reflux is if you need a very, very high activation energy, like the synthesis that we explored in practical 16, the one where you have the reflux setup and the curb clip and all that. That one need reflux setup. But simple things that don't need, things like your oxidative cleavage. Did you have oxidative cleavage of alkenes in practical 15? I'm not sure, but yeah, there were some things that you did in practical 15, the organic QA2 practical, where you remember you collected water from the side bench and then uh you had a warm water bath and or hot water bath and then you just put the test tube inside. Yeah, that's called heat. Don't need reflux. I just need heat to provide that additional energy. So just to be clear, the times where you write under reflux is when you have things like oxidation of primary alcohol, oxidation of aldehyde, all that. Okay, what do you not write under reflux for? One is, of course, this oxidative cleavage. In alkenes, when we first introduced this concept to you, we didn't teach you to write under reflux. So let's just keep it that way. Do not write under reflux for oxidative cleavage. And also, second thing, please do not write under reflux for distinguishing tests. Because distinguishing tests should always be simple, like what you did in your organic QA, both in practical 15 and also in your revision practical to practical 20, I think it is. No, practical 18. Yeah, there's a part on organic distinguishing test. So distinguishing test cannot have complex reflux setup, can only have warm or heat. Okay, please be very clear on this throughout your practical and theory papers also. Okay, I think I've digressed a bit much. Let's go back to the question. So we established that this is a carboxylic acid, right? We can start to draw the structure of the intermediate already. So I have an alkene here. I undergo oxidative cleavage. So this thing here will cleave, correct? So therefore, what will I get? Just copy the carbon skeleton over. So originally I had cyclopentene, right? So that's a bit chopped, sorry. Okay, so obviously 5 carbons like that. This was my original cyclopentene. So I undergo oxidative cleavage. This thing will break in half. Instead, I will get this thing is going to be OH. Likewise, let me just make it a bit less ugly. This is going to be OH. Alternatively, you can just draw it as like that. But I personally prefer to draw it this way because I find it's a lot more intuitive for me if I can show that my C bond breaks and therefore it becomes a CO and CO. But it's up to what floats your boat, as long as you make sure your chemical structure is unambiguous and accurate. That's what's most important. Okay, so that's step 1 and M. Now, from M, we want to convert this carboxylic acid to the acyl chloride. So obviously, this is just simple, right? PCl5. Need heat, don't need heat. Don't need, okay? The other part in your syllabus where you use PCl5 is nucleophilic substitution of alcohol to form chloroalkane. That one also PCl5, that one also don't need heat. Okay, so yeah, please don't write PCl5 warm or PCl5 heat, okay? There's no need, it's just PCl5. I know because your reagents and conditions, you usually include some kind of conditions like warm, heat, aqueous in dry ether. Just writing PCl5 alone might feel a bit inadequate. You might be tempted to think, am I missing something? And then write something else. No, it's just PCl5, okay? That's all. Please don't feel uncomfortable writing short answers. Okay? And thankfully, they do not ask you to give the reagents and conditions for condensation. So we'll just skip over that. In any case, there aren't what acyl chloride and the amine will undergo condensation freely. You just need to have the two of them. There's no need heat, don't need any special conditions, nothing. Okay, now let's go on to the lower part of this. We said already earlier that one of them is oxidative cleavage, the other one is EA. So this one is obviously going to be a step 3. Okay. So if my cyclopentene undergoes EA, what will I get? I will get something along the lines of halogen, right? And then this C bond will become C double bond will become a CC single bond. So I already know that my N is going to be cyclopentane is going to be an alkane. And then presumably I will have a halogen here. Which halogen you want, Cl or Br, really it doesn't matter. But I just, for whatever reason, feel more comfortable putting Br. So it's just HBr, gas, and room temperature. Actually, you don't need to write the room temperature also lah. If you don't write heat or warm, it's implied that it's room temperature, but it's just good practice to include it. And lastly, step 4, I want to go from this to an amine. Okay, because I need to get this P what, then only this thing can undergo condensation with my acyl chloride to form an amide. Okay, so this is nucleophilic substitution. How do I perform nucleophilic substitution of a halogenal alkane to form an amine? NH3 in ethanol and heats. Okay, so that's it for this synthesis scheme. 7 marks, 4 marks here, then 1 mark for each structure. And if you are not very secure, let's just do a final check, okay? We have 5 carbons. This one got 1, 2, 3, 4, 5 carbons. This one, P, also got 1, 2, 3, 4, 5 carbons. So total should have 10 carbons, right? Check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, done. That's it for this question. Thank you.